Yeah. So our for week 3 lectures, our topic is volumetric analysis, and you already have a practical. I mean, in that sense that we have done practical on week 3. I mean, volumetric analysis, the titration. You already have an experience of what we should do for volumetric analysis and how do we do the analysis of acid and base. And the good thing is about that you have been exposed to the problem, and then some of you, I am sure that some of you already visited this lecture slide, many of you. So this is what you do when you start to learn alone, I mean yourself. You explore a lot other than just I show you this is this, this is that. If you do yourself, you explore many more things. So this is one good thing that you explored it, but that's why I'll go through very quick, and I hope that you will you will get the idea better. And I also hope that if you have any question because of solving the problem in experiment 1, you can ask, or you can understand it better, or you can get the answer. So our learning objective for this, I mean, what do we want to get from this lecture? That standard solution, we want to know what is standard solution and what should we do this for standard solution as well. Nishi Mitra, do you have any question? Nishi Mitra, do you have any question? You raise your hand. And Siu, okay, and Siu Xiang, you said that how do you know? I also do not know. The Student Central will allocate you that which group I mean, you please go and check your timetable. What time is your timetable, okay? Nishi doesn't matter. Okay, it's okay, no problem. So, Siu Xiang, please go and check your timetable to which group or which section you belong to, all right? My timetable has 2 slots. That means in the morning and afternoon both group. Then I do not know. Please let them know that there is a problem like this. Maybe there is a mistake. By mistake, they put it like that. Please let them know. Shagor, yeah. Okay, no problem. So can you please repeat where I can see my group? You don't know yet? You go to your canvas under this FAC 10021 chemistry, and then there is a project group. You go and see there is a project group. Okay, better before I start, then I show you first. Wait. Or should I show it afterwards? Okay, this one. The section you created for class. I didn't create any section. Once again, please be clear that I did not create anything. The timetable I did not create. I don't get to create it. If I would create, I would create the most suitable time for me. This time is so difficult. So it is not, I didn't create it. The Student Central, they created it. You go and please ask your SIC that, for you, you go and check your student timetable from the what is the website name? Campus Nexus. Okay, you go and there the Campus Nexus. There you will see that they have student portal, yeah, something like that. they have created a timetable for you. They've already put you in that timetable. All right, so I hope it's okay now, clear. I'm going to the lecture slide. I want to finish it faster today because it is almost done. Okay, so now I was telling that our aim, or what do you want to learn from here, to know what is standard solution and why do we have to bother about the standard solution. How standard is standard. Calculate the number of moles, molarity, and most specifically concentration of solution and acid-base titration. How does this reaction goes on? Why this acid-base reaction happens in the first place, right? That is the thing that we need to know. Okay, so first thing that we have already seen that analytical chemistry means how do we analyze that what material could have been here and or what are the compounds this chemical is made of, right? We know the Panadol, we know that paracetamol, we know that those type of even for antacid or whatever, they are almost similar, they look similar, but what are there inside? How do we find it? That's why analytical chemistry. And right now we are in the wet chemistry. There are two chemistry, wet chemistry and instrument, two section. Wet chemistry that you get to hand your hand in the solution type thing, that you have to make the solution, you have to mix each other. That is the wet chemistry. And instrument is you just take a little bit of those sample and then put in the instrument, and the instrument is, our machine is giving you the not exact result, but it's giving you the data. From the data you have to find out the result. So we have seen the gravimetry analysis. Now we are going to the gravimetry analysis, the precipitation, and then find out the mass of the precipitate. So that is the gravimetric analysis. From there we can find it. For the volumetric is that we do the reaction first, right? And when there is a reaction, there is what do you call it, a solution involved there. And when there is a solution involved there is different ratios or concentration. Okay, so solution and concentration, these two things are important for volumetric analysis. So currently we are in acid-base reaction. We'll say a redox reaction later on. So this is the volumetric analysis, that in both of the solutions should be in aqueous medium, and then the solution, the unknown, should be found out by measuring the volume required to neutralize it, right? Since it is an acid base, so we have to neutralize. If it is an acid, we have to add base. If it is a base, we have to add acid to get it neutralized, because we know that acid and base makes water and salt. And when there is no acid or base anymore, we call it the neutralized solution already. All right. So that is what happens when you drink too much of acidic food, right? And we have the acidity in our stomach, and we feel the chest burning or all those things, and then we feel the throw up, something like that, and then we use antacid. So there is an acid-base neutralization reaction going on. But I mean, we cannot, I mean, we are not physician, but we are chemical engineers, chemists, so we understand we cannot neutralize. If you go and tell the doctor that I want to take antacid because I'm feeling the chest pain, burning, I want to take and neutralize all the acid, the doctor will say, no, you cannot. Because unlike here in the lab, that we do is we just neutralize exactly and full neutralization, no acid or base remnant. But in our stomach, we cannot do that. If we do that, we don't have any other, what do you call it, digestion anymore. We don't have digestion anymore. So what we do is we take just the amount that the excess amount of acid is neutralized, not 100%. All right. So now we are going to that concentration things. the concentration of the solution. Concentration can be expressed in many ways, right? Gram per liter, gram per volume, or molarity, or PPT, ppm, all those things can be expressed in gram. But once again, for chemical reaction calculation, you can prepare a solution in gram per liter, no problem. You can prepare a solution ton per, sorry for that, but 1 ton of solution will not be dissolved in 1 liter, mostly. But what else? You can prepare kg per liter, no problem. But the thing is, when you are going to calculate, right, that how much of the reaction happened, or how much of the each reactant took up each other, then you have to come to that molarity, number of moles, right? Number of moles they have to come, because molarity is the easiest way to find out that concentration of the solution. Easiest way to deal with in the chemistry lab or chemical lab. So the molarity is important for us. And it defines that how many moles in 1 liter of solution. 1 liter. That is two important thing to remember, that moles and 1 liter, exactly 1 liter, okay? And number of moles. If there are 5 moles in 1 liter, we call it 5 molar solution. If it is 0.1 mole of that solution, of that compound, in 1 liter, we call 0.1 molar solution. And this is the equation that we already know, C equals M over V, that is the concentration equal to number of mole over volume. All right, so I'm not spending much time on it, because it says that calculate the amount of mole of solute present in 20 milliliter of 0.255 molar solution. Since C equals N into V, so N will equal to C into V, right? N will be equal to C into V, that is concentration times volume. But once again, I think I told it in the first time. So once again, all these volumes will always be in liters. If you just multiply with this 20 milliliter, your answer will be wrong. So you have to convert it to liter first. Only then you can multiply to get the number of moles. And once again, here is the 3 significant figure. Here is the 3, because this power 10 powered are not considered significant figures, right? Because this is the, since it is negative, it was the 0 before the significant figure after the decimal places. So those zeros are not considered, as if you have followed or were in the session when I was discussing about the significant figures. So only these 3 significant figures are significant. Why this is 3 significant figures? Because here we see that here are 3 significant figures, right? Here is 3 significant figures. Here it is 4 significant figures. And then it comes to the lowest significant figures, that is 3 significant figures here. So significant figures is one of the things. And decimal place is different thing, really. The decimal place is figure after the decimal place, or what do you call it, the dot or point after that point. Like here is 2 significant figures, 2.1, but to 1 decimal place. This is expressed in 2 significant figure. I'm talking about this 2.1 gram, right? Let me take that pointer. Okay, here I'm talking about this one, that 2.1 gram. Here there are 2 significant figures, but 1 decimal places, right? So question B says that calculate the molarity of a solution when 2.1 gram of sodium bicarbonate, you can also call it sodium hydrogen carbonate, dissolved in 1 liter of solution. 1 liter of solution, when it says that our job is much easier already, because 1 liter of solution means whatever number of moles in this solution, That is the number of moles already. So what we have to find it, the number of moles in this 2.1 gram of sodium bicarbonate. And finding the number of moles is easy, as we said here, for last 2 weeks, that number of moles will be found if we just divide it by molecular mass or molecular weight of that compound. Molecular weight of sodium bicarbonate is 84 gram per mole. So if we take 84 gram, exactly 1 mole of sodium bicarbonate is there. Okay, if we take 84 gram of sodium bicarbonate, it is exactly 1 mole of sodium bicarbonate is there. Can anybody tell me how many electrons, atoms, or sorry, how many molecules of sodium bicarbonate is there? Anybody? Can you just type? In 84 gram, how many atoms of sodium bicarbonate are there? Guys, are you listening? I got one answer. Anyone wants to reply? How many atoms in 84 gram of sodium bicarbonate? Time is ticking. 3, 2, 1. Zero. Okay, time's up. I don't know why you say 7 or 6 or this type, but in 1 mole, there are always Avogadro's number of that particle there. If if there is a sodium bicarbonate, atoms, sodium bicarbonate molecules, sodium bicarbonate molecules, there will be exactly Avogadro's number of molecules are there in 1 mole. Okay, so it will be 6.023 times 10 power 23rd number of molecules, right, of sodium bicarbonate will be there. All right. So in 1 mole of sodium bicarbonate, or 1 mole of HCl, or 1 mole of anything, there will be always Avogadro's number of particles there. If it is a molecule, then Avogadro's number of molecules, because sodium bicarbonate is a molecule, it's not an atom, right? Because there are many atoms together, sodium, hydrogen, carbon, oxygen. So all together are forming 1 molecule. So that's why we are calling it molecule, and there will be Avogadro's number of molecules there. If I would say like, okay, 1 mole of sodium, only sodium, nothing else, then there would be Avogadro's number of sodium atoms there, because sodium is not bounded to anyone, just atom. But this sodium, hydrogen, carbon, and oxygen all are bound together, like they are forming 1 unit. 1 unit all together are making 1 unit, and that is why it is called a molecule. So that's why there will be Avogadro's number of molecules there. All right, so now we know that what is in 1 mole, how many molecules, or how many atoms, or how many. In 1 mole of electron, there will be Avogadro's number of electrons. Okay, what in 1 mole of human, right, or 1 mole of oranges, 1 mole of whatever, there will be Avogadro's number of that particular thing. So if 1 mole of human, there will be 1 Avogadro's number of people, one person, I mean, like Bazlul, like who else? Jonathan, Burnham, Rizvi, all those single people, but the total number will be Avogadro's number, 6.023 times 10 power 23rd, if there is a 1 mole of people, right? So this is what, don't be confused with the number of moles and Avogadro's number. If you have any question, you can just ask me. Okay. All right, so this is how we find the number of moles. We just divide the mass by molecular weight of that compound, and then we know that this is the number of moles. And since it says the 1 liter of water, this amount, so it is exactly that number of moles, it's 0.025. Question number 1C, calculate the mass in gram of a solid present in 2.5 and molar sucrose. So this is the sucrose that we eat as a salt, as a sugar, table sugar. So this is sugar, and sucrose is C12H22O11, unlike glucose and fructose. So this is a sugar, and from here it says that I have 2.5 liters, like this bottle. Can you see the bottle? Yeah, my water bottle. So this is a water bottle. Let's say I have 2.5 liter and 2.5 liter of this sucrose solution, but the concentration is 1.505 molar concentration. So how many gram of sucrose I added it in the in the water I add, and then I dissolve it. How many gram? How do you find it? Once again, N equals C into V. If you just remember this equation, is so easy. N equals C into V, so that you can find. Just multiply it with the molecular weight, the number of moles, and molecular weight, so that gram and gram will be cancelled out, because molar is moles per liter, and then from there we find the mole, and here it will be mole as well, and this mole and this mole will be cancelled out. So gram, only gram remains. I think in the PDF version that has been given to you, it is much more, I mean, those gram, moles and gram is written there. Here it should be gram. Pen. So here it will be mole as well. And this mole per, yeah. So this mole and this mole will be cancelled out, and here it will be gram only. So 896 gram of sucrose I had to dissolve. Almost 900 gram of sucrose I had to dissolve in 2.5 liter of water, so that I can get a 1 and 0.5 molar sucrose. All right. So here, other units of concentration, that was in gram per liter. We already understand gram per liter means the mass of solute in gram, and then 1 liter of solution, how many gram. Weight percentage. So weight percentage means whatever weight you have, or whatever concentration, gram per liter or mole per liter, or whatever you have, we express at the end, we express it as weight by weight percentage. That means gram per gram. Okay, gram per gram, and since it is a percentage, 100%. So how many, if I say that weight by weight, that means gram of solute in 100 gram of solution, that's this. So for first experiment that you did was, what was that? Vinegar, right? So it was vinegar, and at the end we found that vinegar was, let's say 0, okay, no, okay, let's say it is a 0.09 molar, right? At the end we find that the vinegar concentration of the vinegar was 0.09 molar. What do we understand? That in how many, I mean, the vinegar, like this in a bottle, it was dissolved, right? The vinegar was put here and then the water was made, put here to made up. So how do you understand that? How many liter of water are there? Anybody? That means 0.09 moles of vinegar in 1 liter, right? Because mole per liter, molarity is mole per liter. So I'm talking about gram weight by weight percent. How do we, from molarity or from mole per liter, how can I convert it to weight by weight? So 0.09 molar, let's say 0.09 molar means moles per liter. Molarity is moles per liter. So 0.09 moles of ethanoic acid will be how many gram? How do we find it? We just multiply it with its molecular weight, right? 60 gram per mole. 60 gram per mole. If we divide, multiply this mole, then this mole and mole cancelled out, and we will have 5.4, right? 5.4 gram, is it? 60, 5.4 gram. That means in 0.9 molar solution in 1 liter, I have 5.4 grams, sorry. I have 5.4 gram of 5.4 gram. So now you see that weight by weight percentage, I already got 5.4 gram of the what do you call it, ethanoic acid or whatever, right? But what about this? I have to express this one as in gram as well. For water, we know that at room temperature, 27, 28 degrees centigrade, around that temperature, water, 1 liter water exactly, 1 milliliter, 1 gram, or 1 liter water is 1 kg of water. So here, it will be 1000 gram as well. It will be 1 kg of water, because 1 liter, so it will be 1 kg, and 1 kg means 1000 gram, right? So from here, and then we multiply by 100, so that we find the concentration or percentage, weight by weight percent. Weight by weight percent. This is how we find the weight by weight percent. We find the weight by weight percent. We can also convert it to volume by volume percent, or weight by volume percent. If it is weight by volume, then I did not have to change the liter, because I already have the liter here, right? And okay, so weight by weight by volume percent also possible, just like volume by weight percent is also possible. Volume by weight percentage is also possible. So in here, for volume by volume percentage, then we will find the milliliter of the solvent. Solute, sorry, solute means which one is dissolved in the water. That is the, for this case, just before the example that we gave for sucrose, sucrose is the solute and the water is the solvent. So weight by weight percent, how many milliliter of that solute is dissolved and in 100 milliliter of the solution. All right. So here we find that for volume by volume percentage, it is chiefly if the solute is not liquid, then it is not applied. This unit is not allowed, not used. If it is the solid that we are dissolving in water, only the solid is dissolved in water, that time it is not used. Mostly weight by weight percentage will be used. But if the solute that I will dissolve in water or any other liquid, that is liquid also, both are liquid, then this volume by volume percentage are used. All right, I think too much expressing here. Okay, so ppm is another concentration, expressed in concentration, that is parts per million. In 1 million parts, how many parts are there? We will use it in not here because this is a very small amount concentration, and this is usually used for environmental and chemical engineering these calculations. So gram of solute per million gram of that solvent, all right, or milligram of the solute per 1 liter of water. That is the weight by volume percentage when we are expressing the ppm. ppb is even smaller, is part of, in billionth. How many parts of that particle in billionth of other particles? So that is the parts per billion, ppb. We will not use these two things for our calculations. Question 1D, it says that convert 0.55 mole per liter HCl into weight by volume percentage. So this is what I was talking, that the volume, the weight percentage, cannot delete, the weight percent, here it is moles HCl, right? It is an HCl, 0.55 mole of HCl, and molar HCl, actually mole per liter, that means molarity of the HCl is 0.5 and 0.55. So now we have to convert this 0.55 moles to gram, and then only we can find it is the weight percentage. How do we make it to gram? So 0.55 moles means how many gram I dissolved in the water, and the same thing, just multiply it with molecular weight, so that we find the gram of HCl, how many grams is there, and from there the water is already 1 liter, that is already in the liquid form, so I don't need to convert anything. If there is in 1000 milliliter is 220.1 gram, then in 100 milliliter how many gram it will be, right? So that is, we can find. So so that it is in 100 milliliter, it will be 2.1 gram or 2.1% of the solution. So far, is there any question? No. All right. Now, if we go to the lab, by the way, I will need your response of who wants or who are okay to come to campus for face-to-face. I will open the poll later on. Okay, so standard solution. Oh, if we go to the lab, that's sodium hydroxide, right? We prepared the sodium hydroxide, we prepared the HCl, how to make the solution, and how much should we weigh it and then dissolve in the water. All those things are, we have to prepare it. But the problem is, I prepare the water, the solution in water and leave it in the lab, and then tomorrow I want to start or use that same thing again. It is not the same, right? It is not exactly the same thing that I prepared today, because at the end, the quality changes. There are many factors, quality changes. So what we call is that there are some standard solution, okay? And we cannot also prepare the everyday everything, right? We cannot prepare everyday everything. So what we can do is we can standardize with a known solution. Like I have to prepare I need to use 1 molar of HCl every day. Like I want to use it for over 1 week. For my research, I want to use every single day. And it is very time consuming, it's not efficient thing to do every single day, right? So what you do is I will prepare a standard solution, and every day I come back, I just check whether the concentration is still okay or become spoiled already, or not spoiled, but whether the concentration changes like yesterday, so that I will be consistent. I will know that what concentration exactly I am using, right? So to what we check the concentration is called the standard solution, right? That is the standard solution, and it is made up of primary standard. Those primary standard, there are some criteria to be a primary standard, and we see that it should be readily obtainable in a pure solid state, not liquid, but pure solid state. That means we can find it in the lab, or we can purchase it for our lab purpose in a solid form, in a powdery form, maybe let's say it's in a powder form, right? It should be a known, it should have a known formula, exactly known formula, that it is a KOH or NaOH or HCl, exactly formula should be known. And it should be easy to store. I mean, it does not need any very delicate process or very delicate arrangement to store it. You can just store it in a standard, like in a room where the temperature is always maintained. We can just leave it here like that, and should not react with the atmospheric oxygen or atmospheric gas, any other gas on a, like you leave it in this form, and overnight it reacts with oxygen or reacts with water from the water vapor from the air, and it becomes, the quality becomes deteriorated. So it cannot be, that will not be a standard, primary standard. It should have a high molar mass. Okay, so high molar mass means 200, 250, around that molar mass, so that what will happen is, if it is the molar mass is very small, 0.1, 1 or 2 gram molar mass, then the problem is, if you want to make 0.1 molar solution, you have to take a very, very small amount, and when you are taking a very, very small amount, there is always a chance of error, right? So that is why we need to, primary standard solution shouldn't be a very small amount, higher molar mass. And of course, should not be that expensive. If it is too expensive, people will not want to use it. Primary standard solution are sodium carbonate and hydrous. That means it does in this molecule, they don't have water molecule in it. So this is the primary standard. Sodium borate, although there are 10 water molecule in sodium borate, that means 2 sodium atoms, 4 boron atoms, and 7 oxygen atoms are there, and altogether 10 water molecules are also associated there. So that is sodium borate, and this is the primary standard. Although there are 10 water molecules, but they are very stable. The water does not go up, go out, or does not evaporate easily, or it does not take more water into it easily. So that's why they are standard. Stable. Acids, those are base. So if I want to standardize my base, I will use either sodium hydroxide. I will use either sodium carbonate, or I will use sodium borate, right? If I want to standardize or know exact concentration of my acid, I will use oxalic acid, that is 2 water molecule in it, or potassium hydrogen thalate. All right, so potassium hydrogen thalate will be using to find out whether it is standard, what is the concentration of that. If if I want to know that what is the concentration of my acid, I will titrate with this base, known concentration of the base. If I want to know the concentration of my base, I will titrate with this acid, because titration has to be two different opposite thing, right? Acid and base. Okay, so, and secondary standard solution is sodium hydroxide. It cannot be a primary because it is very hygroscopic. It takes water. It takes water, that means it absorbs water from the atmosphere. And acids are hydrochloric acid, also sulfuric acid. They are also not primary standard because they are also cannot be found in the solid form in the standard laboratory condition. And HCl, moreover, is a gas. Sulfuric acid is a very hygroscopic. It absorbs water from the solution. Oh. It's almost 1 hour. I have to go a bit first. Stop me if you need to ask question. So this is thing. This is the thing that I was just discussing in the question 2. Question 2a, the answer is given here. The sodium anhydrous sodium carbonate should be used because sodium hydroxide cannot be used as primary standard. It is delinquent. Solution 2b. It says that calculate the mass of a base needed to prepare the standard solution. That means 0.025 molar of the solution and 500 milliliter. Okay, 500 milliliter, 0.2 molar solution. So N equals C into V once again. The number of moles, how many number of moles I would be needed. And I saw it is 0.125 moles in sodium bicarbonate. And the sodium bicarbonate means how many grams, because sodium carbonate, just now I said, we discussed that it is a solid form, right? It is a solid form. So if it is a solid form, then 0.12425 moles that we calculated does not make me know that how many gram is actually 0.125 gram, unless I multiply it with its molecular mass, that is 106 gram per mole, and then it will be 13.25 gram. All right, so I have to take 13.25 gram bases and alkali. No, not same. I will discuss later on. Okay, so here, what I was saying. Okay, so sodium bicarbonate, if I want to know that 0.5 molar, 5 liter of 1.25 moles per liter if we need, I will need 1.125 moles of the sodium bicarbonate, and 0.125 moles of sodium carbonate is 13.25 gram of sodium carbonate. How do we prepare it? This is the round bottom flask. We call it the round bottom flask, RB flask sometimes, RB flask, okay, R and B flask. All right. We put the sodium bicarbonate or whatever, sodium hydroxide inside, and then this is the mark. This is the mark. This mark means if the water is up to this level, it will be 500 milliliter here in the solution. So the technique is you put the solid first, after that you put some water, right? You put some water, I mean just enough water so that it becomes dissolved, and then you swirl it, add water and then you swirl and then you stir it, not stir it but swirl it like this, so that it will be well mixed, and then you put the water, I mean fill up the water to this level, around this level, and then again give a good swirl like this, like you swirl it a bit nicely, so that it will, and then slowly you mix up and go up to this point, not that point. Okay, so go up to this mark, exactly to this mark, so that it will be 500 milliliter of that. All right, so now we go to the acid-base reaction. I will go to 30th slide, and then only I will do the name calling and then distribute the project, because it's almost hour. So acid and base. What are the acid and base? Acid and base, there are two definitions. I mean, there are many definitions. And for these definitions, acid, we will be using the Lewis definition of acid. And the acids, actually, previously we knew about this acid and base definition from Arrhenius, and he says that acid is those who gives hydrogen, and base are those who takes hydroxide. Okay, hydroxyl OH group. But this definition does not satisfy all the acids or base. They do not fall in this, but still they get the act like an acid and base as well. So then Lewis came out, and then they give a nice sorry, I don't know what is happening. Okay, so Lewis came out and gave us a nice definition of acid and base that says that those acid are those what gives you hydrogen ion, and bases are those that takes that rather than giving. They're taking acid. Just one simple formula, that acids, that is proton donor, and base, they are proton acceptor. So that is acid and base. So that is the Lewis definition of acid and base. And from here, if we see that first reaction, that it says that HCl and water. Water, by the way, is a very mysterious thing. Water, it says that okay, water is the substance that can be act as a base or an acid. That is the very mysterious thing about water, that it sometimes, depends on the situation, and the type what they are reacting with. They will be acid. They can behave as an acid and base. So acid is giving water, and base is taking this hydrogen from the acid that is producing. Okay. So from here we see that HCl is giving up the hydrogen, and it is producing the hydrochloride, chloride ion, and water is taking up that hydrogen, hydrogen ion or proton. Hydrogen ion is called as proton as well, because it is no neutron, so there is a proton, only proton here, no electron, only one electron gone. So okay, hydrogen can be called as a proton as sometimes. So hydrogen ion can be called as proton sometimes. Let me drink some water. Okay. So since this hydrogen ion is given up by this HCl, which is an acid, this water is taking up that hydrogen ion or proton, and then it is becoming hydronium ion, and HCl is becoming chloride, so that it becomes an anion. Just let me check who is calling me now. Sorry. Okay, so this is the mechanism of how acid and base goes on. So when acid is losing one acid is losing the hydrogen ion from its molecule, it is itself is becoming a base, right? Let's see, somebody sent something, message. Siu Xiang Liu, I am not mistaken, alkali bases. Yes, alkali that are dissolved in water, and then the bases that does not dissolve in water, but they still behave as a base. Okay, so thank you for that. Okay, so acid is giving out the hydrogen, the proton, and this is taking. So when acid is given up, right? When acid has given up that proton, the chloride ion it formed, it itself becoming a base. Why? Because this chloride ion, since it is a negative charge, so it can, to minimize this negative charge, to normalize this charge, it can take up hydrogen again. So that is why it is a base. So each acid has its, so that's why this HCl, chloride is called as a, this chloride is called a conjugate base, okay? This chloride is a conjugate base of that acid. This is a conjugate base of that acid. And this one, however, can donate one, because it has 3 hydrogen more than, and because of this 3 hydrogen, it becomes positively charged, all right? So to minimize that charge, to get it neutral state means, see here there is no charge, 0 charge. Here also no charge, 0 charge. So to everyone wants to be neutral, not, the higher the charge, the more unstable it is. So when it has charge, it is become unstable. It also wants to give up the hydrogen, and when it gives up hydrogen, that means it can give a hydrogen, and it act on an acid, and whatever gives hydrogen is an acid. So that is why this is a conjugate acid of this water. So H3O is a conjugate acid of this water, and chloride is a conjugate base of this acid. So every acid has a conjugate acid and base, and every base has a conjugate acid. Same goes for here. So ammonia, now we are using ammonia with water. You see that ammonia is a more stronger than, just now we saw that water was acting as a base and reacting with HCl. Now we see that water is again reacting with ammonia and acting as a acid here. Acting as an acid, how? Because this it removed 1 hydrogen. This H2O, it gave 1 hydrogen to this ammonia, and then ammonia becomes NH4 plus. NH4 plus. It is 4. It was 3 here. Becomes 4, and H2O, it becomes OH by giving 1 hydrogen, right? By giving 1 hydrogen, it becomes OH. That means it is deficient of 1 hydrogen, and that is why it is not in neutral charge. But here, by taking 1 hydrogen, it becomes excessive of hydrogen and becoming positively charged. So that what it is, that this hydroxyl is a conjugate base of this acid, because water was acting as an acid here, and this ammonium ion is a conjugate acid of this base because this is a base, so this is a conjugate acid of this base. Because it can lose one hydrogen later on, if need be, it can lose one hydrogen, and this hydroxyl also can take up one hydrogen. Hydroxyl OH negative, it can also take up one hydrogen, so that this is base, right? So now how do we know that strength or acid and base? The more stronger is not that how much it burns you, or it not how much it causes this thing to corrode, but how much it ionizes, right? How much it ionizes in the water. If more 100% ionization happens in the water, that means it is a very strong acid. It's called the acid strength is very high. For hydrogen as well, HCl as well, that HCl, if we put in the water 100%, it will be charge separated. Okay, 100% will be charge separated, and it will produce hydronium ion. It is most of the time we show in this way, that H plus, right, H plus and chloride, H plus and chloride ion. But in actual scenario, this is the thing that happens in actual scenario. But for our easiness or comfort, we just write H plus. So hydronium ion and chloride ion are produced in the water if we put HCl, because this is a strong acid. Sodium hydroxide, sodium oxide, if in water, it will produce, if we produce sodium hydroxide by being dissociated. The water will be ionized, and then hydroxide will be taken up by this sodium oxide, and that is how the sodium hydroxide will be formed. And if sodium hydroxide, if we put in the water, it will produce sodium, okay, sodium ion and hydroxyl ion. All right, sodium ion and hydroxyl ion. So that is why sodium hydroxide is a strong base as well. Weak acid and weak base, they do not dissociate. They very small amount, very small, that's partial, like less than 1%. I'm not giving you a figure, but it's very small. Considering this HCl, sodium hydroxide, they are very strong. They are 100% of them, they get dissociated or ionized in the water. Considering to those, this acetic acid or ethanoic acid, this one, and sodium methylamine. So these are the weak acid and weak base, and they very small amount, just small amount, they get dissociated in the water. And when they dissociate, they form this type of ions in the water. In each of the following equation, question number 3, in each of the following equation, identify the acid and base, name the conjugate acid and base. So this is HSO4, right? Bisulfate ion, it's called, because it is coming from sulfuric acid. Sulfuric acid is H2SO4, right? H2SO4 is the sulfuric acid. H2SO4 is the sulfuric acid. All right, so here one hydrogen is gone from this molecule. One hydrogen is gone, and since one hydrogen is gone, here there is only one hydrogen we see, and one hydrogen gone, that means hydrogen is positively charged, right? Hydrogen gone in a form that H plus is gone, H plus. So since one hydrogen positively charged is gone, so we will have one negative charge excess. It will increase because this positive and this negative charge, when this hydrogen was here, this positive, they cancelled out each other. They cancelled out each other, and that is why H2SO4 was neutral, but HSO4 negative here is a -1 because one hydrogen is gone from here. So when we put in the water, what will happen is what do you call it? This one is hydronium ion, H3O4O plus. The hydronium ion will be formed, and sulfate ion is formed. So hydronium ion is formed. How does the hydronium ion form? Of course, from the water. And this hydrogen gave this compound, that is SO4, gave one hydrogen to this water and produces H3O plus, right? So this is still an acid. This is still an acid. And that is why it is releasing hydrogen ion, or it is donating hydrogen ion to water. So, water is taking up one hydrogen, and then it becomes the conjugate acid of this base because it is taking the proton or hydrogen ion. So water is a base, and by releasing that hydrogen, this acid, this is the conjugate base. Sulfate ion is the conjugate base of this water. Sorry, of this sulfuric acid, hydrogen sulfate. Question number, going to the B again. Question 3B, that ammonia is reacting with sulfide ion. Okay, H is the sulfide ion, is coming from sulfur, is sulfide ion is reacting. This is actually an equal sign, it is not showing this way. Okay, so ammonia is reacting with sulfide ion and it will produce ammonia, right? It is producing ammonia and hydrogen sulfide, all right? Hydrogen sulfide again. So this one is giving sulfide ion one hydrogen. This ammonium is giving one hydrogen to this sulfide ion, and this sulfide ion is taking the hydrogen and become hydrogen sulfur. So this thing, this ammonia is acting as an acid, right? This ammonium is acting as an acid by giving the hydrogen, and this sulfide ion is acting as a base by taking up this hydrogen. And since it is this form, they just left the hydrogen or released the hydrogen. Now it becomes the conjugate base of this acid, ammonium acid. And this hydrogen's HS1, it becomes a conjugate acid of this sulfide ion, because later on from here we can take one hydrogen. We can take out of this molecule. It is possible that we take one hydrogen out of it. So this is capable of releasing one hydrogen from sulfide. So that is why it is this is a conjugate acid of this base. All right, so this is the explanation here. So acid-base titration problem, how the titration is done, we have already, I don't think I don't need to go more. So what is this? In the burette, this is the titrant or titer is there, and in this flask, conical flask, this is called conical flask because this is the cone and it's the flask. So not necessarily 20 milliliter, you can take 25, you can take 10 milliliter, you can take other milliliter also. Okay, so this is the conical flask, and then we add few drops of indicator, chemical indicator, and then start to do titration. We start to add the titrant from the burette, and it should be drop by drop. Okay, to be careful, you have to be very careful. You cannot add in one go, you have to be careful, and by adding every drop and then we swirl it till when the color changes to a permanent something other than the color that we were started. So that will be the titration. Now that is our titration process. And this color depends on different type of indicators and also the pH of the solution that at the end product, pH of the end product. The phenolphthalein in acidic form, it is colorless, but it will be in pink when the medium becomes a bit basic. Okay, alkaline becomes more alkaline. It will be in pink color. Methyl orange, although don't be deceived with the name. Okay, methyl orange, it will be pink color in acidic medium, but it will convert to yellowish, not exactly yellow, yellowish when it is in base or alkaline medium. So this pH range also changes. The phenolphthalein will give you the color change range from 82 to from 8.2 to 10, and methyl orange will give you this pH range. The color will only be visible in this pH range. Beyond or above this, it will not be. Before or beyond this pH range, we will not get the change in color appreciably from this methyl indicator. So that's why we have to be very considerate in when we are choosing the indicator when we do the titration. For us in this foundation program, we will be mostly using the phenolphthalein because it's just good for us. But when we do other things, it will be we have to be careful, and then you know that at the end, what is the pH is going to be for our solution. Based on that, we have to choose the indicator. So yeah, this is what the indicator is. And indicator, how does the indicator work? You may ask that how does the indicator, or why do they change the color? Indicator itself is a weak acid, right? So it's itself a very weak acid, and since it is a weak acid, so what will happen is if there is a strong base, it will act as an acid. But in presence of a strong acid, it will be acting as a base. I mean, it has a dual nature, or whatever you can say. So we will learn later, not now, this class, maybe later on. When we go for degree, we'll learn more about this. Okay, so rinsing the glassware, that is very important. When you do the lab work in our lab, it's very, very important that how do we rinse the glassware? We, the pipette, here is the ideal state. It says that only sodium hydroxide solution. If we are doing a acid-base titration of sodium hydroxide and HCl, right? For this case, in this case, I mean, rinsing the glassware for the case, if we are doing the titration with sodium hydroxide and HCl, or any ethanoic, just like the experiment one we did, ethanoic acid and sodium hydroxide, if we are doing. So in this case, it was asked, I mean, considered. But the ideal practice is we rinse it with tap water first, okay? Rather, we wash it with tap water first. How do you wash it? We, with the pipette filler, the pipette, first we talk about the pipette. The pipette filler, we fill up the pipette of the soap water in the pipette and then release it. Nothing, you don't have to do anything, just fill it up and throw, fill it up and throw for few times, 3-4 times. Why? Because if there is any greasy material or oily substances inside, then this soap water, it will remove that. And then we rinse it with the tap water first, 2-3 times the tap water. Fill it up and throw, fill it up and throw the water. And then once with the just distilled water, all right? Once with the distilled water. And then, if possible, deionized water. After that, we should be, ideal case, we should be washed or rinsed with sodium hydroxide solution. But we are lucky that we have our good lab assistant to help us. They will usually they used to, not every time because it's very hard for them. So we are lucky because our students are good here. When they finish the lab, they usually rinse their pipette and burette and all the glassware, and it is also mandatory here to rinse all this thing with tap water and then with distilled water. So we can go to the lab and then we can just directly follow this, that we this is not ideal condition because we are lucky. So we just wash the pipette with sodium hydroxide solution and throw the sodium hydroxide solution, and then take the solution for measuring. Burette, because in conical flask, I will take the sodium hydroxide, and the hydrochloric acid, I am taking it in the conical flask. I am taking the sodium hydroxide. Oh, here it is already said. Sodium hydroxide I am taking. It is HCl. It is HCl in a burette. So that is why I need to rinse the burette with hydrochloric acid. Rinse it means, you know, just fill it up and then, or just a little bit and then throw it. And the conical flask that I will have the sodium hydroxide in, I should be, oh, my battery. Okay, my battery almost gone. Okay, this conical flask that I will take this sodium hydroxide in later on from that pipette. This is the pipette, right? I should be washing it nicely, thoroughly, because if there is any ions inside, it will react. We do not know what type of ion. It may react with the HCl because they will be ionized. HCl in the solution is ionized. They may react with that or cause the trouble of that reaction. So that is why deionize. But the good thing is we can also use the distilled water and the result is very similar to each other. So this is the titration result from this average thing. And here we use 5 different trials. 5 trials was used, and 1, 2, 3, 4, 5, just like your first experiment. The final burette reading was taken, it was 20.20, and initially we started with 0. That means here in the burette, initially it was, how to say, we fill it up. This is the 0, this is 0, right? 0.0 milliliter. And here, let's say it is 15 milliliter, right? Here it is 30 milliliter, let's say. Actually, it is 50 milliliter. So here we started at 0, and then here is the 0, right? This is 0, and then this is 15. So after we do the titration, let's say 17 milliliter I had to use. So what will happen is how many we added. So HCl we have added to this sodium hydroxide. 17 minus 0 is 17 milliliter, right? If I had started with 5 milliliter and then I added like 22 milliliter, right? So 22 minus 5, I would do like this, 22 minus 5, and then it is how many? Yeah. So 17 as well. So this is a milliliter. So this is how we should be calculating this the titer or titrant. Okay, so and another thing, you see that there are differences. There are differences 6, 4, 8, 2, 7, 8, 8, 6. So which should we take? Which of them? We should be taking those are very close to each other. Ideal thing is if we do the lab, we would take 0.1. The difference between one another is the 0.1 difference. So here we see that this is one we take, this is another one we can take, this is another one we can take, right? If let's say that for this another trial, here we would get 19.83, that is very close to each other. I would take this one as well, right? And then those I am taking, I would tick it. Below that, I would tick it, that this 4 result has been taken. This result, this is no tick here, so this result has not been chosen. So there is no tick here. So this is how we do the average type. This is average titration we are finding. And since I have taken here for this calculation, there are 3 were taken. So 1, 2, 3, and sum it up and divide it by 3. So altogether, we found the final value is 19.82, right? 19.82 is the final value. So calculate the concentration of sodium hydroxide. I'm not going through a lot, but since we found the volume of sodium hydroxide 20 milliliter that we started with from the pipette we added, but HCl I added is 19.8 milliliter. All right. So from there we see that number of moles of HCl is this. And since the reaction is 1, stoichiometric ratio is 1:1, so exact same number of moles will be in sodium hydroxide. So I know that is one. So sodium hydroxide has the same number of moles in this. And from there, it is 20 milliliter, we see. So we know that it is 20, what is the concentration of it? There is question number 5, ethanoic acid content in the vinegar is the exactly same thing that we have done, and I hope that you understood this and you have grasped this is broken. It should be a equal sign here. All right. So this is how we have calculated it. Visualization of question 6. Where is the question 6? Let me check how many do we have? How do I end it? Okay, we do not have many, but I just go through quickly for this. So question number 6 is the commercial concrete cleaner, all right, contains the hydrochloric acid and it has 25 milliliter of this. So it says that the dilute 25 milliliter. Okay, there is one thing, 25 milliliter of the solution, right, was diluted to 250 milliliter. So that dilution factor is a big factor and sometimes you do not consider, so be careful. Dilution factor we have to consider. A 20 milliliter aliquot of 0.448 molar sodium carbonate was placed in a conical flask. Methyl orange indicator was used and the solution was titrated using the diluted core cleaner. The methyl orange indicator changes permanently on yellow to pink at 19.85 milliliter of the cleaner was added. The concentration of hydrochloric acid and the concrete cleaner, we have to find out. From here, 25 milliliter to 250 milliliter, the dilution factor is already 10%, right? I mean 10 times. The dilution is 10 times diluted. From 225, I made it to 250 milliliter. That means I diluted it 10 times. And here 20 milliliter of this molar concentration of sodium carbonate means how many moles I already can count out, find out how many moles I have in 20 milliliter aliquot of this, right? And from the stoichiometric ratio, if we see the reaction, the stoichiometric ratio is 2:1. That means 2 moles of HCl is required to neutralize 1 mole of sodium carbonate. So 2:1. So if I have, how many moles of sodium HCl? So from this, we find out the number of moles of this sodium carbonate. And from here we see that 8.96 times 10 negative third moles of sodium carbonate. The HCl will be exactly half of the number of moles. HCl will be exactly half because 2:1. If 1 mole, I need 2 moles of it, right? Of sodium HCl. So if I have 1 HCl, I have half of this sodium bicarbonate. So HCl is half of it. Sorry, what I'm saying, double, right? So if I have 1 mole, I will have 2 moles of HCl. I have 2 moles, I will have 4 moles of HCl. So this is the stoichiometric ratio, and then we know that we will have just the double of this number of moles of sodium carbonate, in a number of moles of HCl, then the number of moles of sodium bicarbonate. So HCl is having the multiplied by 2 is 0.10179 number of moles of HCl, and this one is in 19.85 milliliter of the solution. So from there we find the concentration already. We convert it to liter first. How do we convert it? We just divide by 1000 to convert to liter, and then we divide the number of moles by that liter. N equals C into V, C equals N over V. And then we find the concentration of this, right? So here we, and now this another thing, that this is not the all, because at the beginning we diluted this solution of HCl, diluted by 10 factors. So these 10 factors we had to multiply. You can multiply this number of moles and then convert to this liter, or you can just directly multiply this one and get the concentration, final concentration. Both way can possible. Question number 6b, if the manufacturer's specification is 33 weight by weight percent of HCl, is your result accurate? Calculate the percentage of error. If 33 weight by weight percent, that means 33 gram, right, of HCl in 100 gram, and 33 gram means how many moles of HCl we have. So that is the number of moles we have in liter. In how many moles of HCl 33 gram means. This is done. And the density, since we have to find out the gram per liter, so the density is HCl, consider 1 gram per milliliter, or just one, simple like water. So 100 gram of HCl will have 100 gram in mass or weight. So 100 milliliter of HCl is having 0.9051 moles of HCl, because it says that in 100 percentage, sorry, is 33%. So 100 milliliter should have this moles of HCl, because 100%, 100 milliliter will have 33 gram. So in 100 milliliter, there are 0.9051 moles of HCl. And then in 1000 milliliter, how many moles? 10 times, so 9.05. And from there, the percentage error we found is the theoretical mass experimental value by the theoretical value. From there, we find this 25%. Oh, sorry, I mean 0.25%. And this is acceptable if the uncertainty or the percent error is less than 5%, it is considered very good. But if it is more than 5%, it is considered not very accurate. The higher the percentage, the higher the error is higher. The higher the error percentage, the unacceptability is higher. But for your thing, I mean, you are giving me the data, you are not doing it in the lab. So what happens is I fabricate the data, so you don't have to worry very much about that is less than 5 or more. Of course, less than 5 is good. So you double check, triple check your calculation if it's okay. If still no, I mean, if still more than 5 after checking many times, then just don't be worried that much. And when we do the experiment, there can be many problem occur. Then there can be many different types of error occur. Those errors, we can divide them into 2 types. One is systematic error, one is a random error. I was briefly talking about it in experiment 1. That is, systematic error happens in one direction. That means it can be prevented, right? It is, how to say it? Like you are using a ruler, right? You are using a ruler like this. I don't know whether you can see it. And measuring the length of a pen. The length of a pen, you are measuring it. And you are measuring it once. So what will happen is, there is a chance that you will not get the exact value of that, of the pen, of the length of the pen. So and also that you do not know whether this is exact the length or the calibration of this ruler is exact or very close, I mean very good or not. So what you have to calibrate, you have to find out whether this ruler is accurate. How do you find out? You have to calibrate it against a standard ruler. That, okay, my 1 centimeter is here, 2 centimeters is there, so whether it is exact same length with the standard ruler or not. So by this way, we can reduce the systematic error. A random error also can happen in all directions. Is called that by how do you call it? So sometimes we take the value you go and measure with a balance, right? You go and measure the balance, you find it 5.05 gram. Another time you take, it might be 5.55 gram, right? Or you are you are taking the solution out by a pipette and you see that it is 10 milliliter, but when you are taking again, you see that it is 9.8 milliliter. It's not exactly 10 milliliter. So, or sometimes you say you take it, it looks like that it is 10.05 milliliter. So it can happen more or less, so all direction it can happen. So that is called the random error, and it can be also reduced by a repeating measurement. So if you take many times and you see that, okay, you have taken 5 times, you measured the water 5 times, 3 times you found it is 9.95, and the other times you found it less or more. So you take these 3 and then do the average. So that is how we can reduce the random error. What are the sources of error? That is the rinsing of glass. If we do not rinse the glassware, then we do not know what is inside already, right? Dirt, impurities, that will cause the error. Detecting the end point. When we do the titration, exact at what point did it change the color? Maybe somebody will see now, maybe somebody will see after 1 drop has been added more, then they will find that this is the end point. So there is a chance by not being able to see it clearly, that is the detect end point. Contamination, that I said, and measuring error in instrument. So if you do not do this standardization or do the test tolerance, standardize the calibrate those instrument that we are using, there are more chances that error can occur. So we have to see, when we fill up the burette, we have to see it, the meniscus, it called the meniscus, not here. We are not taking this measurement, this reading. We are taking this reading. That means 20.35. This one here, it is looks like it's 20.35. Here we are not saying it's 20, right? This value is not 20, it's 20.35. This is the meniscus. We take the meniscus of the level of liquid in a cylindrical beaker or burette or pipette. This is because of the cohesive force of the water. This is not taken. And this is how we should be considering it. All right, we are very close to going to our name roll calling. All right, so question number 7, it says that a 1.2 gram antacid tablet containing 80% by mass of magnesium hydroxide at the active ingredient, what volume of 0.15 molar hydrochloric acid could the antacid tablet neutralize? What volume? So how many volume of sodium and HCl should we be adding to this antacid powder? Antacid. So magnesium hydroxide is reacting with sodium HCl in this form, and then it's producing magnesium chloride and water, right? And it says that 1.2 gram of antacid, but 80% of this is magnesium oxide, hydroxide. So 80% of 1.2 is 0.96. And we know that magnesium hydroxide, the molecular weight of it, and from there we can find the number of moles in 0.96. How was the number of moles of magnesium oxide in antacid? And this is only that count. I told you many times, right? I'm repeating it many times, that number of moles, that is the only thing that counts. And here, here it is 1:2 reactions. So if I need 2 HCl, I will need 1 magnesium. And if I need 1 magnesium, I will need half of this HCl. So, sorry, 2 HCl. So if there is 1 HCl, there is half magnesium. So number of moles of HCl we found out is this, and then just by dividing the volume of they are dissolved in, we can find the concentration, the volume of this so magnesium hydroxide. And this is, so this is for today we discussed. Do you have anyone has any question on it about the about the last slide or about the last problem that we was talking? No? Okay, so now I go to Siu Xian Liu. Okay, so yeah, alkali are bases that dissolve in water. Yes, so many of the bases actually are not water soluble. It's very hard to get them solved in the water. So what we do is we dissolve them in some organic or inorganic liquid, and then we dissolve in water to produce the solution. So those bases that get dissolved in water, that are called alkali, and those are not, they are called just base. So all bases here, he says that all bases are alkali and not all alkali are bases. So this is the rhetoric come from. Okay, so if there is no question, if our error percentage is larger than 5%, do we need to answer the very last question? Is it we don't need to answer the very last question means in the experiment you okay, generally if it is more than if it is more than 5% or less than 5%, what does the less than 5% mean, right? What you tell us, if it is more than 5%, what does it mean? Why what do you understand if it's more than 5%? You just write it down. And why do you think it is more than 5? Where was the problem? Was the data problem, or was in the calculation part problem? Where was the problem, or was it calibration? I mean, just in the discussion, just discuss, not very long, like 2-3 words, sentences. Those are the things that we want to see, that you are trying to understand the thing that we want to know. Okay. And okay, and now, oh, all right. Go to this our name calling. All right. I am calling as it appears it to me from the student list. I don't know. Yeah, you can see now. As it appears, I printed it out. I didn't type it. So I'm calling it according to this form. If anybody is here, if I'm calling their name, if you don't want to talk, just write that you are here, or I mean, how do I know that you are here? You say yes, or you can type yes. Okay. Right. So, Muhammad Anis bin Abu Hassan. No. Please talk. I cannot see and write go together. Xiang Wei Tio. Xiang Wei Tio. Okay. Yes. Good. Carlode. Thank you. Hey, once again, I mean, excuse me if my pronunciation is not correct. Nishi Mitra. Nishi Mitra. I think I saw her just now. Rizvi.
Yeah, sure, present.
Thank you. Hao Liang Sun. Hao Liang Sun. I cannot look and talk. Talk, please talk. Gwenda Yen Weto. Gwenda. Tammy.
Here.
Thank you. Yu Chen Chung.
Here.
Kelvin.
Here.
Entem. Entimesha. Entambu. Ntemesha. Ntambu. Are you here? No. Okay. Yaman Ziwungte.
Here.
Thank you.
It's Iman, by the way.
Sorry?
It's Iman.
Iman. Okay.
Yeah, Iman.
All right. All right. It will be easier for me. Thank you, Iman.
No.
Okay. Sophia.
Here.
Okay. Marjan.
Present, sir.
Thank you. Veran. Veron. Veran Chin Kai Kong. Kai Ong. No. Jia Keki.
Yeah.
Bernice. Bernice, I saw your message. Yeah. Hello, Bernice. Yeah. Okay. I already presented. Cheng Lian Tio.
Here.
Thank you. Megan.
Here.
Jia Wei Sun.
Here.
Angel G. Quinn.
Yes.
Darren Kwang.
Here.
Jun Hian Chia. Jun Hian Chia.
Here.
Thank you. Brendan.
Here.
Adelaide.
I'm also Brendan.
Oh, sorry. Brandon Yong Chern.
Oh, yeah, that's me. Here.
Okay. Thank you. Okay. So there are two Brandon. Okay. Adelaide. Adelaide Jing Yu Yang Ang. No. Shankar Roy.
Here.
Good. Lian Shu Ti. Lian Shun Ti.
Yes.
Okay. Brian Key.
Yes, sir. It's Brian Kong.
Yeah, Brian Key Sian Kong. Okay. Darren Chan Yong John. No. Siu Xiang Liu. Siu Xiang Liu. No. Jason G Cheng Ting. Jason Ting. Jason Ting. No. Lik Seng Tan.
Here.
Thank you. Jonathan Chi.
Yes.
Gabriel.
Yes, sir.
Tania Radzwa Sharon.
Yes.
Thank you. Chuin Chiet Sim.
Here.
Che Wen Kong.
Yes, I'm here, sir.
Okay. Chen Ming Brandon.
That is me. That is me. That is my name. I am the other Brendan.
Okay. Yeah. Brandon and Brendan. Is it Brendan? All right.
It's Brandon.
All right. Okay. So if anybody said that I am also here, then I present out both of them. And Jason say yes. Jason, why didn't you talk? Okay. Once again, Nishimitra is here. I think I saw you here. It's very hard to find out. I mean, after, because it's not giving me the attendance list anymore. It's very hard. I had a very hard time. Okay, so now what I'm doing to you, I am sharing my screen with you. It will not take long, and afterwards I will change the name of your group, project group, to the topic you get. Like who gets solar, I will put their name as solar group. Who is gets wind group. All right. Oh, before that, let me tell you one thing, serious thing. I see that Mohammad Anis, Chun Hui Chan, are you here? Chun Hui Chan. Chun Hui Chan, not here. Yu Chen Chong. Brian, Sophia, these guys, you haven't submitted your lab safety. Okay, so Sagar Kanti Roy as well, you did not submit. Yeman, you also did not submit your lab safety form. Today is their last day. If you do not submit the lab, you will not get the. I will not check your lab report. This is a must. Okay, please submit by tonight. I will open it for you guys. This is the last time I extend it. After this, I will not extend it. So please submit the lab safety. I don't see it. Yeah.
Okay, sorry, sir.
No, I mean, this is one thing that also go and check time to time from, your module. And there is quite many questions was coming out from the students over the weekend. And please refer to the earlier my announcement about the assessment and the requirements. I announced it last week, I think, week 2 or week 1. Already on the announcement, please go and check. It's much clearer when it will happen, how much marks and blah, blah, thing, everything, and lab report as well. So all those things is very clearly given there. All right, now without any time, almost time. So I'm sharing my slide, my screen with you. Where is it? Here. Okay, so first, which group wants to go first? Which group wants to go first? Group 1, okay, me, group 4. Group 4 first replied. Group 4 first replied, want to go first. After this, who wants to go? Group 8. Group 8, number 2. Group, wait, oh my God. Hold on. Group 8 is number 2. Group 7 is number 3. Hey, there is no group 12 for project. Group 1 is number 4th. Hold on. Group number 1, 4th. Group 3 is 5. 5th. Group 2 is 6th. Group 2 is 6th. Group 5 is 7th. And then group 6 is 8th. All right. So I am doing it rather than giving you the control, because it will be a mess again if I give you control. I don't have anything. I don't have any magic. You can see that on the wheel, all the names of these topics have been written out. So what I'll do is just press. That's it. I'll just press, nothing else. So I'm going for first group is group 4. I'm going for group 4. I will just click. All right. I'm not doing anything. My hands are here, okay? Okay. Group 1, your title topic will be nuclear energy. Nuclear energy. All right. So nuclear energy is removed now. So the second is group 8. Group 8, I am doing this for you. All right. You can see. So I'm just clicking it. My hands are here. Geothermal. Group 8 is geothermal. Geothermal. I remove it from there. And now is going for third one is what? Oh, group 7. Group 7 is third. So I am just click and then let it roll and spin. Tidal wave. Group 7 is tidal wave. Group 7 is tidal wave. Third was group 7. Fourth is group 1. So after this, group 1. Hey, where is only 1? Only 2. How many are doing? 1, 2, 3, 4, 5. What was missing? Nuclear gone, tidal gone, geothermal gone. Just a minute. So group geothermal, tidal, nuclear. These 3 are gone.
Sir, it's solar.
Who?
It's solar energy that is missing.
Yeah, that's what I'm saying. That why did it? Did we start with those, or we didn't start with those? Solar energy, and then tidal wave. Tidal wave is also missing. Oh my God. Tidal wave, biodiesel. Biodiesel and Mergen. Yes, thank you, Mergen. Nishimitra, you come now only. Okay, so what do you think, that I should be doing it all over? I can start from here because 3 has been distributed to 3 groups, or you want to do it on, I mean, you want me to do it all over again for everyone? Mergen, say start again, whatever those. Okay, group 7, group 8, group 4. What do you think? You want to keep those or you want to start over again? Okay, good. Thank you. I start over again. So wait, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh my God, time is. Biodiesel, solar, biomass, geothermal, hydropower is there. Hydropower, wind is here, wind already here. Solar, wind, hydro, geothermal, nuclear is missing. Energy is missing. How many? 1, 2, 3, 4, 5, 6, 7, 8. Oh, now it's 8. That makes sense. Solar is here. Solar here. Wind here. Solar energy. Biomass. Biomass is there. Biodiesel is there. Hydropower is there. Tidal wave is here. Geothermal is here. Nuclear is here. 1, 2, 3, 4, 5, 6. Okay. Once again, I'm going for group. Which one was the first one? Group 4. Okay, group 4. Now let me check once. 1, 2, 3, 4, 5, 6, 7, 8. Group 4, going for group 4. Group 4 biomass. Group 4 biomass. What happened previously is I tried myself and then it was removed and I forgot to add it up. And then from there I started. I was looking for many apps that how can I do this. Okay, now going for group 8. Going for group 8. Biodiesel, group 8. All right. Now going for group 7, third.
The nuclear energy is missing.
Sorry?
The nuclear energy is missing.
Sir, I think the nuclear energy is missing.
Why again it started?
Got back.
Huh?
This mean got back.
Okay, I give it to this group 7, right? Wind energy is group 7. Group 7. Okay, I quickly add nuclear energy. How come it is reducing more than I want it to reduce? Tidal, solar, hydropower. Oh my God. Geothermal. Okay, 1, 2, 3, 4, 5, 6, 7, 8. All right, now I'm going for already 3 done. Group 4th is group 1. 4 for group 1. solar energy, group 1. If I remove, oh, okay. I actually was removing 2 at a time. All right, solar energy gone, and then number 4th gone. Number 5th is, who is number 5th? Group number 2 is number 5th. Yeah, group number 2. I'm going for group number 2. Group 2, hydropower. Group 2, hydropower. And now group 2 gone, group 3. 6th is group 3. See, I made a mistake, spelling mistake. It should be geothermal, I did geothermal. So, group 3 is geothermal. Group 3 is geothermal. And the rest 2, who is going what? This is for a group 8. Group 6, group 6, group 6, group 6. Okay. Group 6 is tidal wave. And group 8 is nuclear energy. Okay, I will name this according to this that you get. Jonathan, no, you cannot. Chenming, did your internet provider provide you the service of internet? What does it mean? See, if I would allow you to choose, that this thing will happen. That I want to do this, I want to do that, and then there will be not so it's not in my hand, it's not in your hand as well as thing can be done. So all these things are interesting. All these things are interesting actually. Bernice, you will know this is why we want to introduce it, so that even you think that, okay, I want tidal energy, I want nuclear energy. At the end, we do not know much. We will start to know much. And then if you even not working on the same field, you will know much when we will go for the presentation. So from your friends, you will know, you can ask more questions to your friends as well. Or they can ask you questions to know more about the topic you are working with. All right. A little bit different, Chenming, biomass and biodiesel, a little bit, the production. Of course, at the end, the usage are same, but the production are a little bit different, or the sources are different as well. What we should do with the project? I like this question, Jonathan and Brian. I am lost. This is just the distribution of the project first, and then what you will do, I will time to time talk to you guys, and then you can ask me questions. I do not know many of these, most of these, but I can tell you what you can go and what you can search, what you can find, and then what you can do. All right, so this is the thing, and you should start looking at the topic that you go and search. What is this mean? What does it mean? And how we should be I mean, why does it call renewable energy? What is the good, bad side of this? How to produce? Blah, blah thing. Which is my first. Okay, so it's already, I've taken, sorry for this exceeding 8 minutes. I thought that I can finish it before 6, but okay. So all the best. Thank you very much. And I'll see you tomorrow morning during the lab session, 9 to check the Canvas mail. 9 to 11, yeah. There are two groups. There are two groups. So one is 9 to 11, one is 2 to 4, and I have to talk the same thing both times. Okay. So yeah. Okay. So I will see you tomorrow at 9. Those who have the session at 9, then I'll see you. But sir, I have both times in the time. So you can join anytime you like. You can join in the morning or you can join in the afternoon. I just submitted my form. Yaman, what form is that? Oh, yeah, good. Thank you. Okay, all right, good night. Bye-bye. Okay, see you tomorrow. Take care, stay safe.